We begin by examining the heat transfer of a fluid flowing through a straight, circular pipe. To make these calculations possible, we assume the flow is steady, incompressible, and moving in smooth, laminar layers. Fluid entering a pipe often moves chaotically, but as it travels, the layers eventually settle into a stable, parabolic velocity and temperature profile. At this point, we categorize the flow as fully developed. This stability provides a significant mathematical advantage. Once the profile is fully developed, the Nusselt number, which characterizes the convective heat transfer, stops fluctuating and becomes a predictable constant. Consider a pipe under a constant surface heat flux, like one wrapped in a uniform electrical heater. For fully developed laminar flow here, the Nusselt number is locked at exactly 4.36. As this text confirms, it is independent of both Reynolds and Prandtl numbers. Determining the heat transfer coefficient is a matter of verifying these two conditions, a fully developed flow and a constant heat flux. Now consider a scenario where the pipe is submerged in a large volume of boiling water. This represents our second boundary condition, constant surface temperature. These conditions create different physical realities. A constant heat flux maintains a fixed energy addition while the wall temperature varies. A constant surface temperature fixes the wall's heat while the flux varies. Because of this, the Nusselt number for constant temperature is lower, at 3.66. To find the convection heat transfer coefficient, H, we use a simple relation. Multiply the fluid's thermal conductivity, K, by the Nusselt number, then divide by the pipe diameter. Pay close attention to how you evaluate the thermal conductivity, K. You must determine this value based on the bulk mean fluid temperature. This requires averaging the inlet and exit temperatures of the fluid, rather than using the temperature of the pipe wall. Engineering accuracy relies on how precisely you define the thermal environment before beginning the arithmetic. While circular pipes are the standard for theory, real-world systems often utilize rectangular or triangular ducts. The underlying framework remains the same for these shapes. We simply replace the standard diameter with the hydraulic diameter, which is 4 times the cross-sectional area divided by the wetted perimeter. Let's apply this. Pause and calculate H for laminar flow in a rectangular duct, where side A is 2 and side B is 1. Use constant surface temperature and fluid conductivity of 0.6. Looking at the table for a rectangle with an A to B ratio of 2, we find a Nusselt number of 3.39 under constant temperature. With a calculated hydraulic diameter of 1.33 and our conductivity of 0.6, the final heat transfer coefficient is approximately 1.53. Geometry and boundary conditions dictate the constants, but the logic to solve for H remains consistent. These constant Nusselt numbers do not apply at the immediate entrance of the pipe. This graph shows the transition. At the entrance, the thermal boundary layer is thin, which allows for a high rate of heat transfer. The Nusselt number peaks at the start and then begins a steady decline as the flow moves further down the pipe. As the pipe length increases, this initial entrance effect is diluted. The average Nusselt number eventually settles at the value we use for fully developed flow. Fluids achieve these specific equilibrium states only after they have been given enough distance to stabilize. We can summarize this process into a 5-step checklist for solving any internal laminar convection problem. Step 1. Verify that the flow is steady, laminar, and fully developed. Step 2. Calculate the bulk mean fluid temperature to find the correct thermal conductivity for your fluid.
Step 3. Identify the geometry and calculate the hydraulic diameter if the pipe is non-circular. Step 4. Identify your boundary condition to select the correct Nusselt number. Finally, Step 5. Plug your verified values into the master formula to solve for the convection heat transfer coefficient. Success in internal convection depends on accurately diagnosing the physical environment before selecting your mathematical tools.